Anyway, we start with the short recap of what we saw yesterday. So the idea that we start from a Lagrangian field theory, which means that we have some space of fields on a manifold M, and an action function of, which is the integral of a Lagrangian over M. And out of this data, we produce more structure on the same space, namely, produce closed. So this produces as follows, that delta S M, and write that here M plus alpha M, where these are the terms where no derivatives of radiation appear, and this is compressed, so, and this turns out to be a boundary term. And this omega M, okay, and then in terms of the M, this then, since we want to our work in symplectic work, we project down by taking the quotient by the kernel of omega m, and we produce a space denoted by F boundary of the boundary of m with a symplectic form of the boundary of the boundary. Okay. So here there is a projection map right here. So this is what we have. And, okay. Now, the first remark is that then here we can define the space of solution to the Euler-Lagrange equation. Okay, and then we can project down here to what I call Ln, which is just phi applied to Ln. So this is here. And we saw that this is automatically resolved. This just follows from this effect. Okay, so this is what now? Let me do this. Now I want to discuss a boundary condition. So the choice of boundary condition is first of all the choice of some submanifold L of the space of boundary M. So this is something you have to choose. And it has to be chosen in such a way that two things happen. So first, we want this L to be such that it selects solutions. So we want, for example, one minimal condition is that L intersection Lm is non-empty and the intersection is transversal. So you have the given Lm here, you have to choose some other L here, and so you select a point here, which will be a solution. Actually, well, its pre-image under pi will be a solution. But the other thing is that you want well, the solution to be really a critical point of the action. Okay? So this is done so you can select solutions. Okay? But then we want the solution to be critical point. It is we want delta Sm for the solution to be identically 0. Okay? So this is 0 because we are on an M, but this term is potentially still there. Okay? So then what you have to do, you have to require that somehow this choice of L kills this boundary term. So let me make a simplifying assumption that I made yesterday. So assume that omega boundary is actually exact. And then this, well, this one form here is a pullback of this one. Okay, so in particular, we can write the fundamental equation as variation of S equal to the Euler-Lagrange 1 form plus the pullback of alpha boundary of LM. Okay, and so okay, let me call this inclusion of L. So the second requirement is that the pullback of alpha boundary to L should be 0. Okay. So under this condition, right, under this condition, when you are at an intersection point between L and Lm, this term is 0 because of this condition. Right? And this term is 0 because you are on Lm. Okay? So both terms are 0, which means that what you have is really a critical point of the action. Okay, so these are the possible boundary conditions. Now let's see what happens at an intersection point. So at a given intersection point x, we can write the tangent space of the space of boundary fields as the direct sum of the tangent space to L and the tangent space to Lm. Okay? You can also restrict the symplectic form to these points. So this becomes now a symplectic form on this vector space. And these two subspaces are isotropic. So this is isotropic because this is what we proved yesterday. And well, this condition also implies that this L is also isotropic. If alpha vanishes, L in particular, also omega vanishes on L. So this is another isotropic manifold, which means that the tangent space is also isotropic. So at each point of the intersection, you can split the tangent space of the symplectic manifold as a sum of two isotropic subspaces. Okay?
I'm sorry? The intersection is transversal by the choice of L, like the intersection between...
You want it to be transversal, yeah.
You choose L such that it's transversal.
Yeah.
Okay.
Yeah. Okay. Now the idea is that what we want to do is to be able actually to select every solution, so every point in Lm, by this prescription. So it means that for every point in Lm, we should be able to find some L, right, that intersects it transversal here, and which is isotropic. So the conclusion is that for every point x in Lm, we want Tx Lm to have an isotropic complement. Okay. So now this condition is very strong. Lm is isotropic for general reason, but now we want to require its tangent space at each point to have an isotropic complement. And this is actually means that L must be Lagrangian. So this implies that Lm must be Lagrangian.
Sorry?
Yes?
Could you put down the board?
Yeah, oh, yeah. Actually, in the finite dimensional case, this is equivalent. It's an equivalent way of saying that, for the dimensional reason, the finite dimensional case, you say that these two subspaces are isotropic, right? And so an isotropic subspace has the dimension at most half the dimension of the symplectic space, right? But their sum must be the whole space, so that means that both of them are half-dimensional. So they're both Lagrangian. In the infinite dimensional case, this is actually one of the ways of generalizing what Lagrangian means. Actually, this is probably the strongest way. This is what we call split Lagrangian. There are weaker ways. Well, this strong condition in particular implies that this subspace is maximally isotropic. This is isotropic, and you can add further vectors remaining isotropic. But, well, the other way around doesn't work. So this condition is the strongest one. Okay, so anyway, this says that Lm must be Lagrangian. So now this is not a theorem. So if you start from Lagrangian field theory and assuming that everything is smooth, you can construct Lm and prove that it is isotropic. But now you have to put this as a condition. Okay, so this is a condition for the theory. Okay, so. Okay.
Are there examples of theories that don't simplify this?
Yes, it comes to that in a moment. So, say the definition. We say that say Fm, Lm, so Sm is a good field theory if Lm is Lagrangian. So notice that this is a condition both for the field theory in general and for the choice of spacetime. Okay? So typically for a good theory you should say that, well, for generic choice of spacetimes, Lm is Lagrangian, and then in some theory for any essentially choice of M it is Lagrangian, for some other you have to be careful, there are some bad choices of spacetimes you have to avoid. So let me give you two counter examples. So counter example. So the first is the following. So suppose that you start with some manifold M, Riemannian or pseudo-Riemannian manifold, doesn't matter. And suppose that your space of fields are one form by tensor Rn. So and one forms some M. And okay, so and then suppose that you are given some constants, we call f a b c, with a b c from 1 to n, and say antisymmetric in the lower indices. And then using these constants I can define a two-form which I call f sub a, f d a plus 1/2 f a. So when you put indices, it's component a, b, c, b, c. So this looks like the curvature, but it's not the curvature in general, it's something, some two-form you can define. And then you can define the action to be the integral over m of 1/2 f a star f a. So I still have to contract the indices. So the next ingredient is some pairing. So this eta is some non-degenerate pairing on Rn. Okay, so this is some theory you can write down. It is Yang-Mills theory if these are the structural constants over the algebra and this is an invariant pairing, but this is some action you can write down in general, and then you can apply this procedure to this action, and it turns out that the condition that Lm is Lagrangian actually implies that these constants are structural constants for some of the algebra and that this pairing is invariant. Okay? So if you choose this constant randomly, they're not complementary to the algebra, you find a counterexample to this. So this now also to show you that this condition of having a good field theory actually, well, essentially selects the physical theories instead of some random theory you could write down. Now let me give you another example of a theory which is generically good, but it can become bad if you choose bad space-time manifolds. So this is just complex scalar field theory in two dimensions. So I just need M to be a two-manifold, and here I want this G to be Lorentzian metric. Okay. And the action is just 1/2 integral over M, d phi star d phi, where phi is just a complex valued function over the manifold. Okay. So this is the space of fields. Okay, so this is the usual scalar field. But now what I do is to choose some very bad M. So the M I choose is the following. So is the product of a circle by some finite interval. So, and I will just show you what the metric look like. So down here, it's just the metric as this light cone with time going here in this direction, this time direction. But then this starts turning as you move up, and at some point there is a bad circle. a bad circle where the metric goes like this. Goes like this. So this means that now this becomes time-like. Okay, whereas this bottom boundary is a space-like. But at some point there is a, light-like. At some point there is a light-like circle. And then when you keep going up, this starts moving on, and for example, it starts getting, say, more and more like this, and at the top you say like this, so this becomes now time-like. Now, if you apply this procedure to this space-time manifold, then this LM isotropic. Not Lagrangian.
In this picture, is I like a compactified time, like
well, this is
plus minus infinity?
This is some interval, some fine interval, say from A to B.
Are they like A and B thought of as like time as plus minus infinity, or?
No, this is a closed interval. Okay, so I want to have a boundary. So why? Okay, to make the exercise, but essentially, what is the reason? Well, the reason here. So another example was that somehow the symmetries were bad. You have some sort of symmetries, but like not much compatibility. Here there are no symmetries, so that's not the problem. But the problem is with this space-time geometry, somehow you lose solutions. The idea is that think of like the wave from set of a solution, which means like think in terms of particles. What you have is that they start shooting a particle from here, right? The particle has to stay inside the cone, right? But then at some point it cannot go further here. It stops here. So that means that now this LM doesn't contain enough solutions. So it's much lower dimensional than expected. So it's only isotropic instead of isotropic. Okay? So these are the kind of phenomena that can appear. Okay. And then the other thing is that there are some theories that are always bad, essentially because of their structure, and some that are usually good, but they can be bad on wrong space-time manifolds.
Do you know if, for example, has like an algebraic version?
Yeah, you can extend it in several ways. For example, you can do some sort of mock version of the Poisson sigma model where you don't put a Poisson tensor and things like that. Yes?
For this second example,
yes.
Do you know a counter-example in which the metric is Riemannian?
No, the Riemannian case will work. Yeah. For this kind of counterexample, typically you need the Lorentz metric. And typically having something like around, either in the middle or on the boundary, might create problems.
For example, do we need to mod the space Fm by gauge transformation?
No, not yet. No, this is still completely general. This is completely general. Yeah, I haven't talked because you see this. I mean, I mean, the equational motion are there, solutions are there, but I haven't talked about that yet. This is just somehow the starting point for the rest of the construction. And maybe since one conjecture I still have is that one kind of counterexample like this one, if you try to do something which is not properly supergravity, just take 4-dimensional gravity and couple it to a 1/2 spinor, actually 3/2 spinor, then my conjecture is that this LM being Lagrangian implies that you really have a Majorana spinor, as in the case of supergravity. So how supergravity is selected as the only good theory with spin 3/2 spinors.
Can I ask one more question here? Like this, is it necessary that the space direction is S1, or could it be also R, or like some interval for like this counter?
In this example,
doesn't look like you need it.
Okay, no, but because I want to use compact manifolds. Yeah.
Okay, but it could be also an interval.
Otherwise, you have to put all the conditions.
But it could be an interval.
Yeah, sure. Yeah. Then you have to discuss also conditions at infinity.
Yeah. Okay. I see. Okay. You didn't want to put boundary conditions.
Okay, now So far there was no distinction between gauge theory and non-gauge theory. There is a distinction between good theory and bad theory. Now let's come to the next step. Is that, for example, you think of the example of mechanics. This LM was actually a graph. Essentially, it was a graph of Miltonian flow, but this is not the case here. So, so now let me come to what we would call the Cauchy data. So suppose that your manifold M is a product sigma times some compact interval. Say the specific 0 epsilon. Okay, so this has two boundary components. Both diffeomorphic to sigma, and okay, if you have orientation, then one of the two will have the opposite orientation. Okay, now what I can think of is, okay, the first observation is that in this case, f, okay, actually there is something probably I should have said before, that, okay, raised it here, so let me do it here. The point that when we have this alpha m, right, this was an integral of something on the boundary, so this means that, well, this construction here essentially lives on the boundary. Okay, so the only thing that you see is the boundary, then the only thing that you see is some formal neighborhood of the boundary. Okay? This is the only, in this construction, this is the only thing that you remember from the boundary. Okay, so but in particular, this means that you can just take some codimensional ones manifold and just attach enough open intervals, so to do all of this construction here, forget what happens to the other side, and you can construct the boundary manifold associated with this sigma. Okay, and the other thing is that if your boundary is disconnected, the space of boundary fields tend out to be the product of the space of boundary fields. So in this case, F boundary in the M is actually a product of two copies of F boundary associated to sigma. Okay, so in this case, Lm is really a relation from the first copy to the second copy. Okay, and the question now is whether this looks like a graph or not. Okay, so the point that typically this might be not true, which means in particular that not every point of this F boundary sigma is visible here. Okay. So now what we want to do is to consider the correct space of possible Cauchy data. So this is another submanifold, we call it C sigma of F boundary sigma. Okay, so this is, well, in words, these are essentially the points of F boundary sigma that can be obtained from Lm for some epsilon. Here. Okay. So to be precise, this means, okay, this is set of points C in F boundary sigma, such that there is some epsilon and some point U in the other F boundary sigma, such that the pair CU belongs to L and epsilon. Okay. So these are the points that can be completed to the points on the pair M for some epsilon. Okay. So these are all possible. Say, call this a space of Cauchy data because these are the initial condition that can evolve. Okay. Loosely, this is what it means. Right? The complement of C sigma are the boundary fields that do not correspond to any NM, which means that they cannot evolve. Okay? So this is the correct space, And now the point that in general, being some submanifold, this is no longer symplectic. And so there is something you have to do. So you want to recover the symplectic structure. So what you do is you take the note C sigma underline to be the quotient of C sigma by the kernel of the restriction. So let me call it IC, the restriction to C sigma of the symplectic form. Okay, you mod out by the kernel again, so this quotient will be symplectic again. Okay. Now, again, this quotient might be singular, and actually this usually is singular. So this is the kind of quotient we don't want to do. Okay, but okay, more or less this is what we want to do. Now, what happens is that, well, there are some remarks. So one remark, if the L is non-degenerate, the Lagrange is non-degenerate, then this C sigma is the whole space of boundary fields. Basically, every initial field can be extended to a solution. So basically, this is essentially what distinguishes degenerate theories from non-degenerate theories. In particular, you should expect that in gauge theories, this C sigma should be a proper subspace of this. And the other remark is that if the theory is good, then this C sigma is quasi-tropic. And well, if you don't know what quasi-tropic means, I will tell you in a moment. Okay, there are, okay, I think I can skip this part. Okay, so I can go directly to tell you what quasi-tropic means. And so now the point will be somehow how to desymbolize this quotient of quasi-tropic submanifolds. Okay, so let's see.
We still have bell theories and pick out some quasi-tropic submanifolds?
Yes, inside this way. Yes, you can easily construct something. For example, yeah, 6 quasi-tropic plus. Yeah. Okay, so that is what quasi-tropic means. So suppose that we have a symplectic manifold. And some submanifold of M. There are actually two definitions you can give of symplectic manifold, which in the finite quasi-tropic submanifold, which in the finite dimensional case are equivalent, and the infinite dimensional case they are not. So the first one is the geometric definition. So the geometric definition says that C is quasi-tropic. Means the following, that for every point in C, the symplectic orthogonal to that point is contained in the tangent space. And what is a symplectic orthogonal? So this by definition consists of all the vector, the tangent vector at that point, but possibly in the whole manifold, such that the symplectic form evaluated to this vector v and some vector w in the tangent space is 0. Okay, so these are all the tangent vector to the ambient manifold that pair to 0 to all tangent vector to the submanifold. Okay. And as you see in the definition, in principle, there could be also some transversal vectors. So the condition is that there are no transversal vectors. Okay. So in other words, it's okay to say that the kernel of this can be computed either first restricted to the submanifold or equivalently first considering what happens in the ambient manifold. Okay. There is an equivalent definition in finite dimension, which is otherwise only implied by the geometric definition, which is the following. So let me denote by IT the vanishing ideal of C. So then C is coisotropic, according to the definition, if this vanishing ideal is a Lie subalgebra. Sorry. Yeah, sorry. It's a Lie subalgebra, where this is the Poisson bracket. So what you do is, so if you have a symplectic form, you can construct the corresponding Poisson bracket, and this tells you that if you take two functions that vanish when restricted to C, compute their Poisson bracket, restricted to C, this is against it.
Alberto,
Yes?
isn't it Tx orthogonal including Txc?
Yeah. Okay, now suppose that what this means, so this condition should be familiar to physicists. So suppose that C is the zero locus of some function, say phi 1 up to phi n. Okay? So this condition says that, well, when you take the Poisson bracket of any two of these functions, these should still vanish on the submanifold, which means that it has to be a linear combination of the constraints. K, or Fi, J, K, Phi, K, or these are some functions. Okay. So in terms of local generators, this condition can be translated this way, and this is what like are called first-class constraints. These are called first-class constraints. Okay, so in other words, if you have a good theory, the space of Cauchy data locally is given by first-class constraints. Okay. Clarify. So let me give you now a couple of examples to show how this works. So we start with an interesting example, which is well, electromagnetism. So to show that this reproduces what you expect. So let me do electromagnetism on a trivial bundle. So my space of fields are just one force on the manifold, and the action functional is just 1/2 integral of dA where star dA with respect to some given Riemannian or pseudo-Riemannian metric. Okay, I could do the analysis in this way, but to simplify things, let me go to the first order version, which makes the computation a bit easier, and I decided to see that they are equivalent in the appropriate sense. So this is a different theory where I introduce a second field. So introduce a second field B. So we have a new theory which depends on two fields, A and B, and this B will be a D minus 2 form. So D is the dimension of the manifold. So the new space of fields now contains A and B. And the action is B wedge dA plus 1/2 B wedge star B. Okay. So B is
dA which, sorry, should the second be dA or?
No.
Ah, sorry, with the star.
Okay, so this is a D minus 2 form, so this produces a D form, and then here you use a hot product. Now, why is it equivalent? Just look at the Euler-Lagrange equation. So if you take a variation with respect to A, you get dB equal to 0, and if you take a variation with respect to B, you get dA equal to 0. So if you put them together, you get that essentially D star dA is equal to 0, and is a Maxwell equation. Okay. And vice versa, if you have a solution of the master equation, you can get immediately solution here, just defining B this way. So you can go the way around, just define B to be plus or minus. Okay. So the set of solution is equivalent. So in this, well, this is the first hint that they are equivalent, they are equivalent, but you can even do more. Okay, so now let's see what happens on the boundary. So when you take the variation, right, there is a term of the derivative here, so that means that alpha m turns out to be an integral over m of b by delta a. Okay, and now what you see here is that essentially now, be on the boundary then. So the only thing that you see here are actually the restriction of A and B to the boundary. Okay? So this tells you that the space of boundary fields actually consists of one form on the boundary and D minus 2 forms on the boundary. Okay? This is the only thing you see. Okay? So I will keep calling them A and B. Okay, and the projection map from Fm to this boundary space is just the pullback to the boundary. Okay, so here we have A and B forms on the whole M, you just restricted to the boundary. Okay, now if I write it this way, I can also say, okay, this is the one form on this space. Okay, and so the symplectic form is delta B where is delta A. You can see that it is non-degenerate in the appropriate sense. In method case, you have to be careful. Say what it means to be non-degenerate, but okay, we got that. Okay, now we have to see what is C of the M, or say C of some sigma. What you see here from this equation is that, well, this equation is necessarily satisfied also by the B you have on the boundary. Okay, so this sigma, certainly this equation is satisfied. And actually you can see that nothing more is satisfied. I mean, if you decompose this equation, you can see that this equation essentially tells you, right, how to evolve the fields, but it contains no further information. So these are the only things that you get. So C sigma is selected inside here by this equation. Okay, and you see that, well, this is not this is not symplectic, so you have to do some reduction. Okay. You have to reduce by the kernel of this one form. And essentially, well, the exercise you can do by using Hodge decomposition is that essentially what you have to divide here is by exact form. So here you have that A is equivalent to A plus D of something, and B is only equivalent to itself. See that, you see, if A is exact, when you integrate by part, you get 0 because of this equation, and actually you can see that there is nothing more. Okay, so at the end you see that, so the somehow correct. So this, okay, you say this is the reduced phase space. In this case, consists in imposing the equation dB equal to 0 and modding out by this transformation. So here, probably you recognize the Billian gauge transformation. And well, what is this equation? Well, this equation is just Gauss law rewritten in a different way. Okay, so this is how you recover the user theory. And there is one equivalent way of writing this. You can introduce a function, let me call it JC, to be integral of C dB over sigma, where C is 0.4, which you think is Lagrange multiplier. So you can see that, well, imposing this equation is the same as saying that JC is equal to 0 for every possible C. Or in other words, you can think of a map J from the space of boundary fields to the dual space, to the space of zero forms. So this is a map that sends, say, the pair A and B to the map that sends a C in here to JC of A and B. So this is independent of A, but it doesn't matter, right? So now you can think of this actually the algebra. This is the algebra of gauge transformation. This is dual. So this is a map from the symplectic manifold to the dual of the algebra, and this turns out to be actually an equivariant momentum map. And this construction here is actually marked in the right direction. This is the same as taking J inverse of 0 modulo the group that integrates this is the algebra.
Is this E like the Nautropel-Lacanici field, or?
Well, okay. No, this is just no. It's more a ghost. Yeah.
It's a ghost.
Yeah.
Okay.
Become ghost.
Okay.
So this is the.
But here it's not, it's even, or is it always?
It's still even. Yeah.
Okay.
This is not quite the neuter charge, but it's kind of the neuter charge, right?
No.
It's like some neuter charge port to the boundary or something. No?
That's what Thomas was explaining at the beginning. There is a difference between the what are called local symmetries and the gauge symmetries. This is good. Yeah. Neuter charges correspond. I mean, in the standard terminology, neuter charge corresponds to global symmetry. So it depends what you mean by neuter charge. Okay. The second example is abelian F theory, which is essentially the same as we had here. So it's the same space of fields, the same space of fields here, and in the action we just remove this part. So Sn now is just the integral of the BA. Do you know why this is called BF? It's because this is the curvature, which usually you denote by F, so this is B times F. Okay. Now we can repeat the analysis. It's essentially the same. The space of boundary fields is the same as before. Nothing changes because like it just arises from this term. The boundary one form is this. So this is a boundary symplectic form. Nothing changes. The only thing that changes are the Euler-Lagrange equations, because now the equations are dB equal to 0 and dA also equal to 0. Now the difference that both these equations necessarily restrict to the boundary. So in this case, the sigma becomes the space dB equal to 0 and dA equal to 0. And now we have to see what is the kernel of a symplectic form. And actually it turns out to be, again, by essentially kind of analysis that, well, this shift consists of shifting A or B by exact forms. The equivalent relation is that A is equivalent to A plus dC, and B is equivalent to B plus some D tau, where tau is a D minus 3 form. Okay. So as a result, well, this actually turns out to be H1 of sigma plus HD minus 2 of sigma. So assuming the sigma is, of course, is closed, I would have boundary terms. And this now is a finite dimensional symplectic manifold, unlike the previous case where this is still three-dimensional. Okay. So these are some of the two basic examples. I think we have to. Tudor was talking of this example implicitly. Yes?
In the previous example, like you get the identification of B with B and not the gauge transformation in a sense, is related to the fact.
So here there is no symmetry in B.
Yeah, it's related to the fact that we start for an action that is not, that requires B to be a form and not a connection, because the B star B is not gauge invariant. So that's it. Is it related? In
Well, Mr. B is gauge invariant under this.
Yes, exactly. So this is related. It comes from the action.
Yeah. Because in this case, this is the only equation you can restrict to the boundary. And so you only get these equivalents. Not the other one. Yeah. I mean, in the non-abelian case, we will also transform, but okay, just by the joint action. Okay, I think this was BF. Okay, so I think we move here. I think these were the two examples. Yeah. So now, so this is done, and so. Okay, so now I can finally go to the BFP formalism. So. Okay, so now let's go back to the general situation. So suppose that we have a coisotropic submanifold and we want to make the reduction. So suppose that now we have M omega symplectic and C quasitropic. Okay, now we want to have C underlying to be C modulo, well, the correct quotient. Now, here what you have to do, according to the general definition, I should restrict omega to C and then compute its kernel. But if C is quasitropic, this kernel turns out to be exactly the orthogonal subbundle of C. This is exactly what the advantage is. Okay, so this is the geometric way of doing the reduction. What happens in the algebraic way? Well, okay, let's first observe. Okay, so take again the vanishing ideal. Now, if you have a function in the vanishing ideal, you can compute its Hamiltonian vector field, that means by xg, and you can restrict it to C. Right? So this becomes some vector fields on the submanifold, which is actually a section of this orthogonal bundle, in the sense that if you now take the Poisson bracket of this with any, in the sense that this doesn't have transversal components automatically. This is a property of being coisotropic. So from this point of view, you can think of the functions on this quotient as the functions that are invariant under this. Actually, in the finite dimensional case, this is surjective. You can produce any section of this orthogonal bundle as the Hamiltonian function of some function in the vanishing ideal. So this means that you can think of the function on the quotient and as the invariant function, which means that it consists of all the function f on C, such that the Poisson bracket between G and f restricted to C is 0 for every function G in the vanishing ideal. Now, the other observation that the function on C algebraically are themselves defined as function on M modulo, the vanishing ideal. So what you're doing here is start with the whole algebra, Poisson algebra function. You mod out by the vanishing ideal. The condition that the vanishing ideal is a Lie subalgebra means that it acts on this quotient, and so you can take the invariant part. Okay? Now, there is an observation that since we want to restrict to C, it's not really necessary to have this, this condition to be so strict. So what you can do is to define some other algebra, which I call NC. So these are the function on the whole manifold with the property that their Poisson bracket with the vanishing ideal is contained in the vanishing ideal. Okay? So the difference here is that here I take function on the submanifold with this property, but now these are function on the whole manifold. Okay? And the remark is that if you take the quotient of NC by the vanishing ideal is contained in here because you put something in the vanishing ideal, you stay in the vanishing ideal. So this certainly contains the vanishing ideal. So you can take this quotient. And this quotient turns out to be the same as the other quotient we had before. So infinity of n modulo ad c, and then you take the invariant part. Okay, so the reason is that here first you mod out by the ideal and then you take the invariant part, whereas here you take functions that are invariant up to the ideal itself, so they are not strict invariant, they're invariant up to the ideal, but then you mod out by the ideal. So you get exactly the same. Okay. And the advantage of the second construction is that this NC is automatically Poisson. This is a Poisson subalgebra. You can verify it easily. This is a Poisson subalgebra of the original algebra function. And now I see in here lies as a Poisson ideal. Okay. So before it was only Poisson subalgebra. It was an ideal with respect to multiplication, but only algebra with respect to the Poisson bracket, but now it becomes a Poisson ideal. And so this quotient is a Poisson algebra. And, well, this is also a Poisson algebra because these are the functions on this symplectic manifold, so it's also Poisson. And, well, this construction actually identifies them as Poisson algebras. Okay? So now the idea is to forget the geometric construction, which might be not good because C might not be smooth, and just focus on the algebraic side. Okay? Algebraically, we can forget symplectic manifolds, and we can think that our data are the following. So we start with a Poisson manifold, Poisson algebra. So this is just a commutative algebra with an additional Lie bracket, which is a biderivation with respect to the algebra structure. And we assume that we have some subspace I, which I call a quaisotrope, after Alan Weinstein calls a quaisotrope. So that means that 1I is an ideal in A with the commutative product and is a Lie subalgebra of A with respect to its Poisson bracket. Okay? So this is algebraic generalization that we had so far. Okay, and then what you do that construction, so you define N to be the element A of the algebras such that their bracket with element in I is contained in I. This is automatically Poisson because of this condition contains I as a Poisson ideal, and you are interested in the quotient N mod I, which is in the Poisson algebra. Okay, so this is completely algebraic now. Okay. Okay. You think in terms of Lie algebra, this N with respect to the Lie bracket is what is called the Lie idealizer. That is this is the largest Lie subalgebra of A that contains I as a Lie ideal. Okay? So it's somehow the Lie algebra version of the normalizer of a subgroup. Okay. So now is you're interested in the cohomological version. I'll say cohomological resolution. Because the problem that this C underline usually is very singular. So the idea is first step, go to the algebraic construction. So in this case, it's NC mod IC. This always works, but it could be still too bad because this might be, I don't know. Take for example when this quotient is not Hausdorff, and basically you can like then typically this quotient just becomes R, and so it doesn't tell you anything about the quotient. So the idea is to do something better. Instead of taking the quotient, is realizing the quotient as a cohomology of some complex. Okay, so the idea is now realize n mod I as H0 of some complex, well, which also some Poisson structure. Okay, so to be precise, what we need is some graded Poisson algebra. Well, which typically contains the original A subalgebra in degree 0. Then we need an inner derivation Q of degree +1. So inner derivation means that the bracket is some element, so the function necessary of degree 1. And moreover, you want this to be a differential, if you want Q squared to be equal to 0, and this actually gives the, for degree reason in this case is equivalent to saying that S bracket S must be 0, and this is what is called the master derivation. Okay? Now, suppose that you are in this situation. Now you want to go to the cohomology of Q. This is automatically a graded Poisson algebra. Right? Because of this construct, because Q is an inner derivation. And in particular, HQ in degree 0 is a Poisson algebra.
Sorry, what do you mean by inner derivation?
Sorry?
What do you mean by inner derivation?
It's a derivation obtained as a bracket.
Okay.
It's something.
Okay.
So I mean, it has to be a derivation of both the product and the Poisson bracket.
Yeah.
And I want it to be inner with respect to the Poisson bracket. Okay, so out of this, something in general, you can construct a Poisson algebra as a zero cohomology. Now, the construction here, so we want this, well, A and S, such that the cohomology HI is the origin is this quotient and I if I is equal to 0 and 0 otherwise. Well, this would be a true resolution. Actually, typically, typically you solve it in a different way. So typically, you're satisfied if this is 0 when I is negative. You cannot get 0 for I positive typically, so it's not really a true resolution in mathematical terms. Sometimes you keep having something in the negative degree and, well, you're happy. Some people are not happy, so what you do is that then you kill it artificially. You introduce by hand new generator to kill the negative cohomology, and at the end. So, I mean, you can always achieve this situation, but sometimes it's not. It's just a question of taste. Okay, now I want to show you that it's possible to do this in the particular case where our algebras was the algebra of Poisson algebra of functional symplectic manifold, and the data here I, this I is a vanishing ideal of quasi-tropics on manifold. So, but I will do this after the break, and we will do the DFT construction.
So 5 minutes, so how long? How long is the break?
I don't know, 3 minutes.
Yeah.